Hi, today we will discuss conjugate beam method. This is developed by a German professor Müller Breslau in 1865. He used to find slopes and deflection due to bending of beams. Take note that this method is based on principles of statics only. If we compare the internal loadings with the beam theory, you can see the change in shear with respect to x is equal to minus w for the internal loading, and this is equivalent to the beam theory, that is the change in the slope theta d theta over dx is equal to m over ei. Also, for the internal loading due to second derivative of m with respect to dx square, which is equal to the change in slope dv over dx, which is equal to minus w, the second derivative of u over dx square, which is equal to d theta over dx, is equal to m over ei for the beam theory. Actually, Professor Breslau take advantage of these similarities of the internal loadings and the beam theory. So if we have to integrate those values, the shear for the internal loading will be equal to the negative integral of w dx, which is equivalent to the angle theta, which is the integral of m over ei dx. For the internal loading, the moment is the double integral of minus w dx, which is equivalent to the displacement in beam theory, which is the double integral of m over ei dx. For the conjugate beam, actually this is a fictitious beam of the same length. Take note, fictitious beam of the same length as the real beam, loaded with the real beam's m over ei diagram. So here you need to determine first, or you need to draw first the moment diagram of your beam, but you need to divide your moment diagram by product ei. Here you will see from the real beam angle, or the slope of the real beam, is equal to the shear of the conjugate beam, and deflection of the real beam is equal to the moment of the conjugate beam. So this way, we need to determine first the moment diagram of the beam, and of course the the supports will have a corresponding supports for the conjugate beam, and I will show that to you later. But as you loaded the fictitious beam with the m over ei, you can just simply compute the shear at a particular point, and that would be the slope of the real beam. And if you take the moment at that particular point, that result will be equal to the deflection of the beam at that point. So here we define conjugate beam corresponds to a real beam is a fictitious beam of the same length as the real beam, but it is externally supported and internally connected, such that if the conjugate beam is loaded with the m over ei diagram of the real beam, the shear and bending moment at any point on the conjugate beam is equal respectively to the slope and deflection at the corresponding point on the real beam. However, we need to change the supports of the real beam to corresponding conjugate beam. As you can see here in this table, if in real beam the support is pin, then there's no problem, because in the conjugate beam the support is also pin. What's the effect of that? In the real beam, for a pin support, there will be no deflection, so delta is equal to 0. But for the conjugate beam, the bending is equivalent to the deflection of the real beam. So since the deflection is equal to 0, then the moment at the conjugate beam should also be equal to 0. So that is why it should be a pin support connection. Except for the slope, of course, there will be rotation for the pin in real beam, but in this case it will also give us a shear for the conjugate beam. For a roller support in the real beam, the conjugate beam, it's also a roller. Again, there will be no deflection or y displacement for roller. That's why the deflection of the real beam is 0. So with the moment of the conjugate beam equal to 0, except for the slope of the real beam, which is unknown, and the shear of the conjugate beam, which is unknown. Another type is a fixed support. For the fixed support, both the slope and deflection is equal to 0 for the real beam. And this is corresponding to a pre-end in the conjugate beam, because at pre-end there will be no shear and there will be no moment. And this is the opposite of a pre-end in the real beam where the theta or the slope and deflection is unknown. So with the conjugate beam, it should be fixed. So the shear and the moment are both unknown. So just remember this one. Real beam pin is the same as the conjugate beam pin. In real beam roller, it should be roller in the conjugate beam. For a fix in real beam, it should be pre-end in the conjugate beam. And a pre-end in the real beam, it should be fixed in the conjugate. Also, other supports just like the internal pin. In the internal pin, again, there will be no displacement, so delta is equal to 0. So what would be the possible support that should give us a moment equal to 0? Then that should be so a hands or internal hands, because the slope is unknown, so the shear should also be unknown. So perfect is a hands. Internal pin is the same as the internal roller. It will give us no displacement. So what support, particularly in the conjugate beam, that will give us a moment of 0? So that's again internal hands, where theta is unknown in real beam and shear is unknown in the conjugate beam. And this is the total opposite if your real beam is internal, connected by internal hands, because in the internal hands there is both rotation and deflection. So what particular support in the conjugate beam that will give us shear and moment? That particular support will be internal roller. For an example, we have this simple beam with pin and roller. From real to conjugate, they are the same. For roller and internal hands, again, for the roller or pin or hand support, they are the same from real to conjugate. But for the pre-end, from the real beam, it should be fixed in the conjugate beam. But for the internal roller, it should be internal hands in the conjugate beam. Again, just think of something that for a hands, the support will never translate y and x displacement. So the displacement or the deflection is equivalent to m. So what support in the conjugate beam that will give us no moment? That is the hands. So with the pre-end has a slope and a deflection. What particular support in conjugate beam that will give us moment and shear? That is a fixed end. Also, for another example, we have this real beam, fixed end in conjugate pre-end, internal roller in the real beam, internal hinge in the conjugate beam, internal hinge in the real beam, internal roller in the conjugate beam. Hence, in the real beam should be the same as in the conjugate beam, which is also hence. And there are other examples here. I hope you will check this one so that it will give you some insights on how to apply the conjugate beam. As an example, we would like to determine the slope and the displacement at point C for the particular beam. A simply supported beam with a hinge support at A and a roller support at B, loaded with 10 kips at the center. The beam has a length of 20 feet and the concentrated load is applied at the midspan. We can assume that the modulus of elasticity is 30,000 psi and the moment of inertia is 300 n's to the power 4. So take note about the units because it's very important. So here in our example, we need to convert first the real beam to conjugate beam, and aside from that, we need to draw first the moment diagram. So before drawing the moment diagram, you have to compute the reaction. And since this is symmetrical, both form and the loading is symmetrical, just take half of the loading 10 over 2, that is 5 kips. So the moment or the reaction at A and B are both 5 kips. And you can just draw the moment diagram directly by using the method of superposition at point C. So if you take point C as the fixed end, then the support at the reaction at A will create a triangular moment which is equal to 5 times 10, that's 50, and at the other side the reaction at B, that's 5, will also create a bending of 5 times 10, that's 50 kipfoots, which are the same. So here is the moment diagram that I am talking about, and aside from the moment 50 kip per foot, you need to remember you have to divide it by the factor or the product EI. So that is why this is not simply a moment diagram, but it's an M over EI diagram. Remember that one. Then after determining the moment or M over EI diagram of the whole beam, we now need to convert the real beam to the conjugate beam. Take note that the length of the real beam is the same as the length of the conjugate beam, except for the supports. And since we have a hand support from real, it's the same as hand support in the conjugate beam. For a roller support at the real beam, it should be the same as a roller support at the conjugate. So the result will be something like this one. Yeah. The loading, the M over EI that we have drawn should be the applied loading of the conjugate beam. So this is the crucial part. I hope you understand this one. You just have to draw the moment diagram of your beam by using the method of superposition. That would be much easier. Of course, you can also draw the moment diagram using the classical method, but that's the problem because how to determine the area and the centroid, that would be more difficult. But if you have to use the method of superposition, it will give us a simpler moment diagram. So in this case, you just have to divide it with the product EI. After determining the moment diagram using the method of superposition, assume that to be your conjugate beam loading. Remember the sign. It is positive. Bending moment is a positive loading on the conjugate beam. And since our moment is positive, then the load 50 over EI should be up, okay? So the direction should be up. So the reactions at A and B should be downward. So to determine the reaction, you just simply determine the resultant of the loading, that the triangular loading. That's 1/2 of the height 50 over EI keep put times the length of the beam, that's 20 feet. And divided by 2, that would be the resultant. That's 50 times 20 divided by 2, how much? 500. Divided by 2, that's 250 both keep. Here it is. That's how I do it because it's just symmetrical. But you can also use the equilibrium equation by summing moment at A, which is equal to 0. So you have the loading FCE times centroid 10 feet plus BY over 20 feet. So BY is minus 250 keep put square over EI. Again, you really have to take care of the units because it will give you a wrong numerical value if the units are different. Again, the result is negative because it should be going down. If you sum up the forces vertical, summation forces Y is equal to 0. So we have FCE plus BY plus EY. So EY is the same, that is minus 250 keep put square over EI. So now we want to cut the section C or the point C because we want to determine the deflection and slope at point C. So we will cut it again. Again, it's just a classic way of doing things. Make a cut, okay? That's the method of section. You can choose either the left figure or the right free body diagram. It doesn't really matter because the result will be the same. So here we cut point C and we choose the right diagram. So here we need to include the shear so that this should be in equilibrium, and we have to include the moment. Of course, the shear and the moment are both unknown in this case, but we have the reaction and the loading, so we can just directly compute the shear and the moment. If we take moment at point C, which is equal to 0, we have minus MC plus the loading 1/2 of 50 keep put over EI times 10 put times the centroid 10 put over 3 minus the reaction 250 times 10 divided by EI. So you can now compute for MC. The moment MC is minus 0.32, and so first after substituting the value of E and I. So again, you really have to take care of the units here. After that, you can also compute the shear by summing up forces Y is equal to 0, where shear in this case is equal to 0. So we are done with computing the internal moments and shear at section C. Remember that the displacement of the beam at point C is equal to the moment at point C on the conjugate beam, and the slope is equal to the shear in the conjugate beam. So in this problem, the displacement at point C is equal to the moment at point C on the conjugate beam, that is negative 0.32 of an hence. And the slope at point C is equal to the shear in the conjugate beam, which is equal to 0. That's how we use the conjugate beam method. Actually, it's very, very intuitive. It's quite nice to use this method to compute for simpler beams and loading. That's all for the conjugate beam method, and thank you for listening.